Hello. Today we are going to be dealing with inverse trigonometric functions and their derivatives. So we know what inverse trigonometric functions are. There are cos to the minus 1, sine to the minus 1, tan to the minus 1 are inverses of our sine, cos and tan. And they have slightly unusual looking derivatives, but we just need to know where to look for them. We're looking on page 25 in our log tables, and anytime you're getting the derivative of an inverse trigonometric function, you're always going to end up using, or basically always going to end up using, the chain rule. And you're going to use it explicitly in this case because it gets quite fiddly to picture what you need to do if you try to do it out the implicit way. So if you see inverse trigonometric functions and you're doing derivatives, we're going to page 25 to get our rules, and we're also going to need our explicit chain rule. Now, let's just do an example and see how this plays out. So we have y is equal to tan to the minus 1 of 3x all over 4, and we want to know what dy dx is. So I recognize that I've got an inverse trig function, so I go to page 25 and I see that I'm using this rule here, but I don't just have x divided by a, where a is a constant, so a would be a number like 10 or 3 or something like that. I don't just have x all over a number, I have a more complicated situation, so I need to use my chain rule. So what we're going to do is use the explicit version of the chain rule. So I'm going to change my y. I need to define a v that is the inner function. So my v, using the chain rule, is going to be 3x all over 4. That is my v, and therefore my y becomes, or my u as we would write it here, is going to be tan to the minus 1. Sorry, it's going to be tan to the minus 1 of v over 1. Now there's a little bit of memory work to do here. It is important, for not making a mistake, that we would write this as v over 1. Because that means that a is 1. One of the difficulty with using the implicit chain rule, which we would often use, is that we have our constant underneath here is the number underneath the line. So trying to do the implicit chain rule would get quite confusing. You'd have to flip fractions on quite a regular basis, and it would get quite involved. So it's safer to use the explicit chain rule like we are here. We now have our u in terms of v, and now we can use our chain rule from page 25. So we have v, we need dv dx. We get our derivative here. This is just 3/4 multiplied by x to the power of 1, so we just end up with 3/4. And du dv, the other thing we need, well, this has been set up so that it's just using the rule in our log tables. So we just end up with a being 1. So the number dividing our variable is 1. It's just 1 all over 1 squared plus v squared. And have everything in brackets whenever we're doing our substitution. And then we don't want this really in terms of v, we want it in terms of x, so we are going to rewrite that as 1 all over 1 squared is just 1 plus 3x all over 4 to be squared. We're going to simplify this down a little bit so that we have less mess to deal with when we bring everything together. So we end up with 1 all over 1 plus 9x squared all over 16. We want to write this as a single fraction, so we are going to end up with a fraction divided by a fraction. So we turn the 1 into 16 all over 16 is equal to 1 all over 16 plus 9x squared all over 16. Flip the fraction and multiply. That's 1 on 16 all over 16 plus 9x squared. That's basically simplified down. So let's do our dy dx. Is u dv, we found here, it's just 16 all over 16 plus 9x squared multiplied by dv dx, which is 3 all over 4. I recognize I have a common factor of 4 top and bottom, and my fractions multiplied together. So I divide out my common factor of 4, and I am left with dy dx being 12 all over 16 plus 9x squared. Now, this math has gotten very abstracted. It's important to link back with what we've just found. This is a function that we can put in different values of x into, and we'll get different values for our function. So this is a normal function. It's a slightly odd function, but it is a normal function. And dy dx gives us the slope of the tangent to this curve, the slope of the tangent to this function for different values of x. If I sub in different values of x, I will get the slope of the tangent to this function at that value of x. And it's important, as we are dealing with more and more abstract functions, that we keep that anchor for ourselves, that this is what we're finding. This is a normal function, and then this is the slope of that function at different values of x, or the slope of the tangent to that function at different values of x. Now, let's do another example. Here, it follows exactly the same setup. Anytime you do the inverse trig differentiation, it's always just going to be using the explicit chain rule and our rules on the bottom of page 25. So let's set up our v in this case. So v is going to be the stuff inside of our inverse trig function. And then what does our f of x become? We write it as u. It's going to be written as u is written in terms of v. And we remember that we should write it as v over 1, so we remember that the value of our a is 1. So we want dv dx. We have our chain rule here. We know we want dv dx and du dv. dv dx is just going to be 3. And our du dv, the derivative of u with respect to v, is going to be following our rule here. Minus 1 all over square root of 1 squared. A is 1. Minus v squared. Everything put in brackets so that we don't make any sign mistakes if they become important. Now, what's v? We want it in terms of x. So we have minus 1 all over. 1 squared is just 1 minus 3x minus 2, all to be squared. We need to square out this bracket. You can do this when you have written out f dash x if you want, or we can simplify it out separately. There's no hard and fast rule. It's whichever you feel more comfortable with. We have 1 minus square the first by the second and double it. Square the second. I have some, sorry, that's in brackets, my apologies. I have some multiplying out I need to do. Minus 9x squared plus 12x minus 4. And I now have this all simplified down as much as I can. And plus 12x minus 3. And I'm now in a position where I can do my dy dx, or my f dash x, is going to be my du dv du dv times dv dx, which is just 3. So I end up with minus 3 all over square root of minus 9x squared plus 12x minus 3. It's worth noting there is technically a common factor of root 3 top and bottom, but you wouldn't need to worry about that in an exam. You could take out a common factor of root 3 here and on the top, and you'd end up with minus root 3 on the top. But you do not need to do that. That would be considered perfectly simplified. So again, this gives us the slope of the tangent to the curve of this function at different values of x. And anytime we see an inverse trigonometric function, this will always be the setup. Use your explicit chain rule to define your v and your u, and then use your rules on the bottom of page 25. And that is what we need